Hello everyone, welcome to the fifth video of this lecture series. So first, this is our first problem today. So the problem states that we have a trial wave function which is given, and we have to find the ground state energy of a one-dimensional harmonic oscillator using this trial wave function. So this problem belongs to the concept of variation method in quantum mechanics. So what is variational method? So let me first introduce you to the concept of variational method. So there are very less number of cases, very few certain cases where we can find exactly the analytic solution of Schrodinger equation. In most of the cases, like in case of molecules or all this, so where we were not able to find the analytic solution of the Schrodinger equation. So then we can use a trick known as this variational method. So this trick is used to estimate the energy of the ground state of the system. So variation method is used to estimate the ground state energy of the system. So how we are doing this? So first we have to choose an unnormalized trial wave function. And suppose this trial wave function is phi n, and it is a function of a parameter. So basically this is called our variational parameter. So parameter, that means we have to find its value somehow. So this is a variational parameter. So using this wave function, we have to find the energy, ground state energy. So energy will be psi h psi. So we have our Hamiltonian. So we will have to, so since this is unnormalized, so we have to normalize this, and obviously this is E is a function of an. So now we have to minimize this with respect to those parameters. So there can be more number of parameters, so like a1, a2, a3 and all this. So we have to minimize this with respect to those parameters. So in this way we will proceed. So in our given problem, we have our trial wave function as psi x. It is given as a square minus x square, and we have also 0. So this is for minus a to a, and this is otherwise. So this is our trial wave function. So here a is the variational parameter, and a is the normalization constant, which we have to find by using normalization. So after so using this wave function, we have to find, so this is the process. We have to find energy as a function of a, then we have to minimize this with respect to a, and we have to find the value of a, and by using this value we will get our estimated ground state energy. So let us proceed. So first we have to normalize this wave function. So psi star psi. So this is our normalization constant. From minus infinity to infinity, this should be 1. So we are getting a square, and this psi is 0 outside this region. So our integration limit will be minus a to a, and we have our a square minus x square term. So this is squared. So let us find the value of a squared. So this will be like this. So this will be, the integration will be a to the power 4x minus 2/3 x square x cube plus x to the power 5 by 5, and limit is from minus a to a 1. So we have a squared, and since these are odd in power of x, so we can write this as 2, and this limit can be from 0 to a. So if we put a, then we will have a to the power 5 minus 2/3 a to the power 5 plus a to the power 5 by 5. So this will give us 2a squared multiplied with, this will be 15, and here we have 15 minus 10 plus 3, this into a to the power 5. This is our a square value. So we will get in here 2a squared multiply with 8 by 15 a to the power 5 1. So our a squared will be 15 by 16 a to the power 5, and a will be, like, if we have to find the value of a, it will be root under this. So this is our value of a. So using this, now we have to find the value of h, the value of Hamiltonian. So expectation value of Hamiltonian can be written as a summation of expectation value of kinetic energy and expectation value of potential energy. So what is the expectation value of kinetic energy? So it is minus h cut square by 2m. It will be minus a to a psi star x del to psi del x square psi x dx. So let us evaluate this first. So we have our psi x to be a into a square minus x squared. So d psi dx will be minus 2ax, and d2 psi dx square. Since psi is only a function of x, so its partial derivative and total derivative will give us the same result. So this will be minus 2a. So t will be minus h cut square by 2m, and this term will give us minus 2a. So just write this down outside. So minus 2a, and we have minus a to a psi star dx. So it will be h cut square a by m, and we have another a for psi. So let us take this out, and we have like 0 to a square minus x square dx. So it will be h cut square 2h cut square a square by m into, it will be a squared x minus x cube by 3, and limit will be from 0 to a. So if you do the calculation, it will be h cut square by m, and a square we have value root over like 15 by 16 a to the power 5, and here we have a cube common, and it will be 1 minus 1/3, so that will be 2/3. So this will give us the result 3, it will be 5, and in the lower part we have 4. So we are getting 5 h cut square by 4 m a squared. So that is the expectation value of kinetic energy. Now we have to find the expectation value of potential energy. So what is the potential energy of our problem? So this is a one-dimensional harmonic oscillator. So for one-dimensional harmonic oscillator, we know that potential is given as half m omega squared x squared. So expectation value of V will be minus a to a psi star V psi dx, and we have our term a squared, it will be minus a to a. We have our psi star psi to be a squared minus x squared, its whole squared, and V is half m omega squared x squared. So this is an even function. So we can write this, we can take 2 out. So this 2 and this half will be cancelled out. So we will get a squared m omega squared, and 0 to a, we have our this value to be a to the power 4 2a squared x squared plus x to the power 4. This will be multiplied by x square. So that integration we have to evaluate. So let us do that. So it will be a to the power 4 x cube by 3 minus 2 by, so this is x to the power 4. So here will be 5 and a square a to the power 5 plus here it is x to the power 6. So it will integration will give us x to the power 7 by 7, and limit is from 0 to a. So let us put the value of all this m omega squared a squared. We have value of 15 by 16 a to the power 5. We have a to the power 7 common. So here we will have 1/3 minus 2/5 plus 1/7. So what will be the value? We will get 15 m omega squared a squared by 16, and here we have like 105, and it will be 35 minus 42 plus 15. So this will give us 7, and this will give us 8. So 8 will cancel out, and here will be 2. So basically this is m omega squared a squared by 14. So we have our expectation value of energy to be expectation value of kinetic energy and expectation value of expectation value of potential energy. So kinetic energy expectation value is this 5 h cut square by 4 m a square, and we have expectation value of potential energy to be m omega squared a to the a squared by 14. So we have to now minimize this with respect to a. So let us do that. So delta, so dE dA. So what will be the value? It will be minus 5 h cut squared into 5 h cut squared by 4m, and here will be 2, and here it will be a cube, plus we will have m omega squared a by 7. So that will be 0. So it will give us the value of like 5, it will be 2. So 5 h cut squared by 2m a cube is equal to m omega squared a by 7. So from here, a to the power 4 will be 35 by 2 into h cut by m omega whole square. So we have our a squared to be root under 35 by 2 multiplied with h cut by m omega. So what will be the value of energy? If we put the value of this a squared here, so we will get the value of our energy. So energy value will be 5 h cut square by 4m, and put us this value of a squared. So it will be root under 35 h cut, here will be root under 2, and we have m omega here, and potential energy term is 5 m omega square by 14 is multiplied with this 35 by 2 h cut by m omega. So we have to just simplify this, and it is easy to do. So m will be cancelled out, so 1 h cut will be cancelled out. So, and in this case also m will be cancelled out and 1 omega will be cancelled out. So we have our h cut omega as common, and here we have, like, if we take whole thing under root, so it will be 25 into 2 by 16 into 35. For the second term, we will have root under 35 by 2 multiplied with 2 14s. So this will be 2, this will be 5. And in that case, we will have, this is 7, this is 5, and it will be 8. So it will be h cut omega root under 5 by 56, and here we have root under 5 by 56. So we are getting h cut omega into 2 5 by 56. That means root over 5 by 14 h cut omega. So that should be our the ground state energy using a trial wave function. So let us check. Yeah, so our correct option is B. So this is our correct answer. So this is one type of problem that appeared in various exams. Like you will be given a trial wave function, and you will be given the Hamiltonian of the system, or rather here it is told as an harmonic oscillator. So you know harmonic oscillator potential. So you will be, with this information, you have to find the ground state energy using this variational method, and it is like quite doable and easy. So what you have to do, you have to first identify the variation parameter. First of all, you have to normalize the state, then you have to identify the variation parameter, and you have to find the expectation value of energy and minimize that with respect to that variational parameter to get the value of this parameter, and by using the value you will get the estimated ground state energy. So if you calculate this, so this root over 5 by 14, so we know that ground state energy of a so the harmonic oscillator solution is analytically doable, and its ground state energy is half h cut omega. That means this value is 0.5, and if you calculate this, so this value, like, you can check what will be the value, and this two will be like almost equal. So if your trial wave function is very good, then you will get an almost equal number for the ground state. So that value is almost in the order of 0.58 or something. So this is almost similar. Now let's move to the second problem. So the problem states that we have a particle of mass m in a potential, harmonic oscillator potential, and we have our lowering operator. So in the Heisenberg picture, we have to find dAdt. So what is Heisenberg picture? So before starting with the problem, let me tell you about this different picture in quantum mechanics. So basically in quantum mechanics, we are interested in expectation value on operator because this is an observable quantity. So and this variation with time of, so we have an operator A. So the variation with time of A, it can be considered as equation of motion. So variation with time of A, it can be considered as equation of motion. So that is why we are interested in expectation value on operator. Now this variation with time of A, it can be obtained due to one of the following situation. So what are the situation? So we have first situation where the state vector changes with time, but the operator remains constant. So this is called Schrödinger picture. So in JEST we can write as the state vector, it changes with time, so it is function of time, but our operator, so denote operator by O, so this is not a function of time, so this is a constant. So this is called Schrödinger picture. And another situation is, so operator changes with time, but here the state vector remain constant. So this is Heisenberg picture, so which we have to evaluate in the question given. So in JEST we can write as operator changes with time in Heisenberg picture, but our state vector, it doesn't change with time, so it is a constant with time. And we have another picture which is Dirac picture or interaction picture. So here both operator and state vector changes with time. So that means operator is a function of time and state vector also is a function of time. So this Dirac picture, it is useful for perturbation problems. Like we have our Hamiltonian to be a summation of free Hamiltonian and perturbed Hamiltonian. So in that, if that is the case, then if we consider this interaction picture, then our calculations will be easier. So we're not going into great details about this interaction picture. We will just briefly discuss about the Schrödinger picture and Heisenberg picture. So first we will discuss Schrödinger picture. So here state vector changes with time, so and its time dependence is given by the Schrödinger equation. So S denotes for Schrödinger picture, and we have our Hamiltonian to be this. So that is how our state vector changes with time. So generally we consider Schrodinger picture when our Hamiltonian is independent of time. If Hamiltonian is time dependent, then we consider this Dirac or interaction picture. So if Hamiltonian is independent of time, we can write psi st as this. So this is how the state changes with time in Schrodinger picture. So if we have, so we have kth value of psi to be psi s0, and we will have e to the power I h t by h cut. So this is our Schrodinger picture, and now let us move to the Heisenberg picture. So in Heisenberg picture, time dependence is completely taken care by the operator. So in how it is taken care of, so suppose we want to find the expectation value on operator. So what we will do, generally in Schrodinger picture we have this. So this is our Schrodinger, because generally first we consider that this this operator is independent of time, and we will have this. Now we can substitute this and this by this. So if we write down this, we will have psi s0 e to the power I h t by h cut. We have our as, and we have e to the power minus I h t by h cut, and we will have psi s0. So this we can write as AH, that means in Heisenberg picture. So that is how our operator evolving with time. So e to the power IHT by h cut, we have our AS, and e to the power minus IHT by h cut. So so if we write A as this, psi Heisenberg, A Heisenberg, psi Heisenberg. So here psi Heisenberg is psi s0. So psi s0 we can write as e to the power IHT by h cut psi st. For we are substituting this from here. So basically this is our Heisenberg picture. So the expectation value is same in both the cases, like in Heisenberg picture and also in Schrodinger picture. So why this should be same? Because this expectation value is an observable quantity. And this interaction, this picture, this Heisenberg picture or Schrodinger picture, these are mathematical tools. So which mathematical tool we are using, that shouldn't affect our observable quantity. So the expectation value of any operator, so we can calculate this by consider the Heisenberg picture or by consider the Schrodinger picture. In both the cases, the expectation value of any observable quantity, I mean expectation value on operator, it must not change. It should be same. So it is same we are getting from the calculation. So now we know that in Heisenberg picture the operator evolves with time. So how it will change with time? So we can calculate this from here. So AH we have e to the power IHT by h cut. We have AS and e to the power minus IHT by h cut. So we have to find out this derivative. So first we will have IH by h cut e to the power IHT by h cut AS e to the power minus IHT h cut. So this is first term. There will be another term. It will be e to the power IHT by h cut AS, and we will have IH by h cut, and there will be another term. So it is IHT by h cut del AS del T e to the power minus IHT by h cut. So if we look closely, so now this Hamiltonian and this is also a function of Hamiltonian. So these two, they commute. So we can put this h inside. So we will have I by h cut e to the power IHT by h cut HAS e to the power minus IHT by h cut, and in the second term we will have e to the power IHT by h cut ASH e to the power minus IHT by h cut, and we will have another term as this. Now, if you look carefully at this expression, so we can write this as e to the power IHT by h cut, and so h we can put this side. So this e to the power IHT by h cut AS e to the power minus IHT by h cut. So that is basically our AH. So this expression is giving us HAH. So, and similarly we have to evaluate this. So this expression, if you do in same way, so it will give you AHH. So from the first two expression we are getting 1 by IH cut. If we consider 1 by IH cut, then we have AHH minus HAH, and we have the last term. So we can write this as delta del T of AH. So we have our equation to be change of A with time. It is 1 by IH cut. So basically this is commutation relation of AH and H. So 1 by IH cut AH commutation relation with H, and we have another term. So that is how in interaction picture, in Heisenberg picture, operator changes with time. Now this term, so this has no explicit time dependence. If there is no explicit time dependence, then it will be 0, and we will have DAH dt as 1 by IH cut AH H. And we have another last picture like Dirac picture or interaction picture. So let me just briefly write how we in Dirac or interaction picture we write operator and state. So in interaction picture, state is written as e to the power I H0t by h cut psi st, and we have operator as e to the power I h0t by h cut as e to the power minus I h0t by h cut. So what is h0? So in Dirac picture is useful for perturbation theory. So h0 is the free Hamiltonian or unperturbed Hamiltonian, and h dash, it is the perturbation that we added to the unperturbed Hamiltonian or free Hamiltonian. So this is free Hamiltonian. So this is the expression we use when we treat perturbation theory. So now these are brief introduction to this different kind of interaction. So let us move to our problem. So in our problem we have to find the expectation, the change of lowering operator in Heisenberg picture. So we have to find this. So this will be delta A delta t plus 1 by I h cut A h. Now we know that in case of harmonic oscillator we can write h as h cut omega A dagger A plus half, and this is our number operator. So why we call this number operator, that I have explained in one of my previous video, so you can watch that. So this is our number operator, because if we add this on our any state, it will give us the value of that excited state, and the state will remain same. And we have A to be, so 1 by root over 2 h cut m omega x plus ip. So basically this is our lowering operator in terms of x and p, but we don't need in terms of x and p. So we have Hamiltonian in terms of raising and lowering operator. So let us evaluate this commutation relation. So AH would be, so we have our A and we have our h cut omega A dagger A plus half. So what will be, so using properties of commutator that I have also explained in one of my videos. So we will get A dagger A, and we will have A commutation with half. So commutation of any operator with a constant value, it should be 0, because constant value always commute with this. So this is, we are getting 0, and from this one we are getting A dagger AA plus A dagger A. So that we are getting. Now this is also 0, because both it is commutation relation of A with A, so this must be 0. And we know that A dagger, this is 0. Sorry, this is 1. So this is the standard commutation relation that you can find in any quantum mechanics book. So if this is 1, so then we have AH is h cut omega A. So, and also A doesn't have any explicit time dependence, so delta A delta t, this is 0. So what we are getting? We are getting change of A with time is equal to 1 by I h cut into h cut omega A. So h cut is cancelled out, so dA dt is minus I omega A. So that is how A changes with time. So let me check what is the correct answer. So yeah, this. So this is our correct answer. So this is brief introduction to different kind of interaction picture. So these are like different mathematical tools to make calculations easier. So generally we are interested in expectation value of an operators, because this is an observable quantity, and we saw that in both in all the cases, like in Heisenberg picture or Schrodinger picture or even Dirac or interaction picture, the expectation value of any operator, it doesn't change. So you can use any of the tools. Generally, if we consider perturbation theory problems, then it is always useful, or it is always easy to work in Dirac or interaction picture. So that is it for the fifth video. So we will meet on our next video.